Welcome on No Science channel. Today, we would focus on how we could measure and understand events or phenomena and their impact on our reality. We will go smoothly to simplify and learn how to use statistics. So, today, we're going to answer the question: what is statistics? This is an introduction and a quick review on statistics. Let's get started. Statistics is important in science. It is a crucial process behind how we make discoveries in science, make decisions based on data, and make predictions. Statistics allows you to understand a subject much more deeply. Statistics is all about making sense of data and figuring out how to put that information to use. We could say that statistics is the science of learning from data. So, statistics helps you use the proper methods to collect the data, organize it, employ the correct analyses, and effectively present the results. Finally, we could define statistics basically as collecting, organizing, analyzing, interpreting, and then presenting data. Uncertainty is a fundamental idea in the field of statistics. There are many situations that we encounter in science, or more generally in life, in which the outcome is uncertain or is involving imperfect or unknown information. In some cases, the uncertainty is because the outcome in question is not determined yet, as we may not know whether it will rain tomorrow. While in other cases the uncertainty is because although the outcome has been determined already, we are not aware of it, as we may not know whether we passed a particular exam. So, many scientific studies make use of data. Statistics is concerned with the use of data in the context of uncertainty and decision-making within. Variation is the other fundamental idea in the field of statistics. You have to know that any measurement or data collection effort is subject to a number of sources of variation. By this, we mean that if the same measurement were repeated, then the answer would likely change, as intervariability in measures from a tester to another. So, statistics attempt to understand and control, where possible, the sources of variation in any situation. Statistics is a highly interdisciplinary field, as many other disciplines of science are building their findings on the usage of statistics. However, a lot of people, even among scientists, are afraid of statistics, as they could use mathematics. So, it is correct that statistics is a mathematical body of science that pertains to the collection, analysis, interpretation or explanation, and presentation of data, or as a branch of mathematics. However, some consider statistics to be a distinct mathematical science rather than a branch of mathematics. Two main mathematics concepts are important. First, probability, which is a mathematical language used to discuss uncertain events, and probability plays a key role in statistics. Second, modelization, which allows to build a mathematical model that embodies a set of statistical assumptions concerning the generation of sample data and similar data from a larger population. A statistical model represents, often in considerably idealized form, the data-generating process or the reality, a projection of the reality. These mathematical concepts lead to build tools or softwares that would help any user to apply statistics in various fields. So, in applying statistics to a problem, it is common practice to start with a population or process to be studied. Applied statistics provides our way of thinking and our approach to extracting the most information from numbers with uncertainty. It emphasizes an understanding of the problem or industry. Applied statistics follows a process that folds together the domain and statistics. Here is the catch. The thinking comes first, and then we decide what tools apply. The choice of tool is driven by the objective, the structure of the data, and the nature of the uncertainty in the numbers. So, let's stop being statophobic and open your mind. Statistical analyses are used in almost all fields to make sense of the vast amount of data that are available. Even if the field of statistics is not your primary field of study, it can help you make an impact in your chosen field. Chances are very high that you'll need working knowledge of statistical methodology, both to produce new findings in your field and to understand the work of others. There is a high demand for statistical skills in a wide variety of areas, and as said John Tukey, the best thing about being a statistician is that you get to play in everyone else's backyard. The interests are quite broad, and statistical knowledge provides the tools to understand all of them. A statistician is a person who works with theoretical or applied statistics. He is someone who uses mathematical techniques to analyze and interpret data and draw conclusions. So, what does a statistician do? The following. Determine the questions or problems to be addressed, decide what data is needed to answer questions or problems, determine methods for finding or collecting data, design surveys or experiments or opinion polls to collect data or train others to do so, analyze and interpret data, report conclusions from their analyses. Statisticians offer critical guidance in producing trustworthy analyses and predictions. They can help avoid a wide variety of analytical traps which produce unreliable results. These are small taste of potential problems and analytical errors that can affect a study. Biased samples. An incorrectly drawn sample can bias the conclusions from the start. For example, if a study uses human subjects, the subjects might be different than non-subjects in a way that affects the results. Overgeneralization. Findings from one population might not apply to another population. Unfortunately, it's not necessarily clear what differentiates one population from another. Statistical inferences are always limited, and you must understand the limitations. Causality. How do you determine when X causes a change in Y? Statisticians need tight standards to assume causality, whereas others accept causal relationships more easily. When A precedes B and A is correlated with B, many mistakenly believe it is a causal connection. However, you'll need to use an experimental design that includes random assignment to assume confidently that the results represent causality. Learn how to determine whether you're observing causation or correlation. Incorrect analysis. Are you analyzing a multivariate study area with only one variable? Or using an inadequate set of variables? Perhaps you're assessing the mean when the median might be a better. Or did you fit a linear relationship to data that are nonlinear? You can use a wide range of analytical tools, but not all of them are correct for a specific situation. Violating the assumptions for an analysis. Most statistical analyses have assumptions. These assumptions often involve properties of the sample, variables, data, and the model. Adding to the complexity, you can waive some assumptions under specific conditions sometimes, thanks to the central limit theorem. When you violate an important assumption, you risk producing misleading results. Data mining. Even when analysts do everything else correctly, they can produce falsely significant results by investigating a dataset for too long. When analysts conduct many tests, some will be statistically significant due to chance patterns in the data. Fastidious statisticians track the number of tests performed during a study and place the results in the proper context. Numerous considerations must be correct to produce trustworthy conclusions. Unfortunately, there are many ways to mess up analyses and produce misleading results. Statisticians can guide others through this swamp. Statisticians have long played a role in research and academia. Recently, however, there has been a spike in demand for statisticians in business due to the proliferation of data generation and collection across industries, and because businesses are now realizing the value of data-driven decision-making. In order to be successful, statisticians typically have a unique combination of technical, analytical, and leadership skills. Analytical skills first and foremost, statisticians must be experts in statistical analysis. They must have a keen eye for detecting patterns and anomalies in data. Technical skills to effectively collect and manipulate the data that informs their actions. Statisticians must leverage computer systems, algorithms, and other technologies, meaning technical proficiency is critical. Communication skills. Although statisticians are experts in mathematics and statistics, they must also exhibit strong communication skills to effectively communicate the findings of their analysis with others in their organization. This includes both verbal and written communication, as well as the ability to present data in easy-to-understand, visual ways. Leadership skills. Truly effective statisticians must be able to think critically about the data that they are analyzing through the lens of key stakeholders and executives. Learning to think like a leader can help statisticians identify trends and data points that can make a big difference in their organizations. We could divide statistics in two broad categories: descriptive and inferential. They are important for different purposes. Interestingly, some of the statistical measures are similar, but the goals and methodologies are very different. Descriptive statistics, well, they describe what the data show. Descriptive statistics usually include things like measures of central tendency, where the middle of the data is, and measures of dispersion, how spread out the data are, like distributions. Numerical descriptors and standard deviation, depending on the data types. We go from huge amounts of data that are less intuitively meaningful to compressed and summarized data. Inferential statistics, well, they allow to draw meaningful conclusions about the entire population. Statistical inference uses patterns in the sample data to draw inferences about the population represented, accounting for randomness. These inferences may take the form of Answering yes/no questions about the data, hypothesis testing, estimating numerical characteristics of the data, estimation, describing associations within the data, correlation, and modeling relationships within the data, for example, using regression analysis. Inference can extend to forecasting, prediction and estimation of unobserved values, either in or associated with the population being studied. It can include extrapolation and interpolation of time series or spatial data, and can also include data mining. In terms of theory in the field of statistics, we could have two different approaches. Frequentist statistics views probability as the limit of the relative frequency of an event after many trials. For any given event, only one of two possibilities may hold. It occurs or it does not. The relative frequency of occurrence of an event, observed in a number of repetitions of the experiment, is a measure of the probability of that event. Bayesian statistics, based on the Bayesian interpretation of probability where probability expresses a degree of belief in an event. The degree of belief may be based on prior knowledge about the event, such as the results of previous experiments, or on personal beliefs about the event. Variation leads to numerous observations, expressed by different possible variables. If there is a single variable, what we call univariate. So unit, meaning one, variate, variable. Once you get other variables involved, relationships between variables are created and things become much more complicated. However, there are methods for multivariate situations without too much difficulty. History of statistics and its founders. During the Islamic Golden Age, between the 8th and 13th centuries, mathematicians and cryptographers produced the earliest writings on probability and statistics. Al-Khalil, 717–786, 8th century, wrote the Book of Cryptographic Messages, which contains the first use of permutations and combinations to list all possible Arabic words, with and without vowels. Al-Kindi, 801–873, 9th century, wrote the manuscript on deciphering cryptographic messages, a detailed description of how to use statistics and frequency analysis to decipher encrypted messages. This text laid the foundations for statistics and cryptanalysis. Al-Kindi also made the earliest known use of statistical inference and, with others, developed the early statistical methods for decoding encrypted messages. Ibn Adlan, 1187–1268, 13th century, made an important contribution on the use of sample size in frequency analysis. The first European writings on statistics were done in 1663, 17th century, with the publication of Natural and Political Observations upon the Bills of Mortality by John Grant. The mathematical foundations of modern statistics were laid in the 17th century with the development of the probability theory by Girolamo Cardano, Blaise Pascal and Pierre de Fermat. The term statistics, found in 1749, 18th century, in Germany, and designated the systematic collection of demographic and economic data by states. The scope of the discipline of statistics broadened in the early 19th century to include the collection and analysis of data in general. The modern field of statistics emerged in the late 19th and early 20th century, and the first stage, at the turn of the century, was led by the work of Francis Galton and Karl Pearson, who transformed statistics into a rigorous mathematical discipline used for analysis, not just in science, but in industry and politics as well. Galton's contributions included introducing the concepts of standard deviation, correlation, regression analysis, and the application of these methods to the study of the variety of human characteristics, height, weight, among others. Pearson introduced moments, Pearson's correlation coefficient, p-value, Pearson's chi-square test, principal component analysis, among many other things. Galton and Pearson contributed greatly to biostatistics, then called biometry. The second stage, of the 1910s and 20s, was initiated by William Seeley Gossett and reached its culmination in the insights of Ronald Fisher, who wrote the textbooks that were to define the academic discipline in universities around the world. Fisher developed rigorous design of experiments models, the analysis of variance, ANOVA, and is known as one of the three principles. The final stage, which mainly saw the refinement and expansion of earlier developments, emerged from the collaborative work between Egan Pearson and Jerzy Neyman in the 1930s. Neyman first introduced the modern concept of a confidence interval into statistical hypothesis testing and co-revised Ronald Fisher's null hypothesis testing with the type 2 error and power of a test in collaboration with Egan Pearson. Today, the use of modern computers has expedited large-scale statistical computations and has also made possible new methods that are impractical to perform manually. Statistics continues to be an area of active research as analyzing big data. So this was an overview about statistics, and I hope that was helpful. Please, to subscribe now to your channel No Science. And above all, help us to do more topics that interest you. Leave us your recommendations or wishes in comment. Thanks for watching.